Wanted to work a problem that involves the de Broglie wavelength of matter waves. We first discovered that light waves also exhibit particle-like properties. We've now found that matter particles also exhibits wave-like properties. And the de Broglie wavelength is the matter wavelength of a particle of matter, like an electron, like a proton, like a neutron, or like you or I. We all have a de Broglie wavelength. So in this particular problem, we're told to consider two particles. One particle is an electron that has a mass that's about 9 times 10 to the minus 31 kilograms. The other particle is a bowling ball that we're told has a mass that's about 6 kilograms. We're told that both the very light electron and the much heavier bowling ball have the same kinetic energy, 4.5 electron volts. And from that information, we're going to figure out what the de Broglie wavelength, the matter wavelength of the electron is and of the bowling ball is. So I'm going to do this calculation in 2 steps. Firstly, I'm going to calculate the momentum of the electron, momentum of the bowling ball, knowing the kinetic energies of the electron and bowling ball. And then once I've got the momentum of the electron and the bowling ball, I'm going to figure out the de Broglie wavelength of their matter waves based on the relationship between the momentum, which is a particle-like property, and the wavelength, which is a wave-like property for our matter that exhibits wave-like and particle-like properties. Now, one beginning remark is that the electron with kinetic energy 4.5 electron volts is a non-relativistic electron. Its speed is much smaller than the speed of light. Likewise, the bowling ball, with just 4.5 electron volts, is a non-relativistic bowling ball. Its speed is much smaller than the bowling balls, than the speed of light. And so I can use for the bowling ball, and I can use for the electron, I can use the non-relativistic expression relating kinetic energy and momentum. And so that's what I'm going to use here as I calculate the momentum. So the kinetic energy of the electron can be written as the square of the momentum of the electron divided by twice its mass. This is just an alternative way of writing 1/2 mv squared for the kinetic energy. I'm just replacing the v with the p, replacing the velocity with the momentum. Likewise, for the bowling ball, the kinetic energy of the bowling ball can be written as the momentum of the bowling ball squared divided by twice its mass. And so again, I can use this relationship between kinetic energy and momentum to figure out the bowling ball momentum. So let's go ahead and do that. If I rearrange the equation over here on the left-hand side, I'm going to get the electron's momentum is equal to the square root of 2 times the mass of the electron times the kinetic energy of the electron. And likewise for the bowling ball, the momentum of the bowling ball is 2 times the mass of the bowling ball times the kinetic energy of the bowling ball. And I know the mass of the electron and the bowling ball. I know the kinetic energy of the electron and the bowling ball. So all I need to do at this point is to plug in the numbers for the masses, plug in the numbers for the kinetic energies. And so let me go ahead and do that. And so upstairs here are the numbers for the electron, and here are the numbers downstairs for the bowling ball. Let me explain these numbers a little bit, especially because I didn't put in the units, because I was trying to cram the equations in on this one line. So in the square roots, we've got 2 times in both cases, followed by the mass. So 9.1 times 10 to the minus 31 is the mass of the electron in kilograms, and 6 is the mass of the bowling ball in kilograms, multiplied by the kinetic energy in both cases. Both kinetic energies were 4.5 electron volts. And then finally, what's this number over here? This is a conversion factor between the units of joules for energy and electron volts for energy. So this conversion factor is converting my electron volts into joules. The electron volts will cancel out, and I'll be left with the units of joules for the energy. And so if we look in here, all these quantities, all these values have units, SI units now. And so now I can carry out these calculations. For the electron, the momentum is 1.1 times 10 to the minus 24. And the units, so the SI units of momentum, which are kilograms, meters per second. So that's the electron. And then for the bowling ball, the momentum is 2.9 times 10 to the minus 9 kilograms, meters per second. So these are the 2 momentum. Next step then is to calculate the corresponding wavelengths for these 2 momenta. So I'm going to calculate lambda E for the wavelength of the electron, lambda B for the wavelength of the bowling ball. And these wavelengths are determined by the de Broglie equation, which is the ratio between Planck's constant and the momentum of the electron, or the momentum of the bowling ball. And so all I've got to do now is fill in Planck's constant. I'm going to fill it in again in SI units. So that's 6.6 times 10 to the minus 34 joules seconds. And I need that both for the electron and I need it for the bowling ball. And then I'm going to divide by the momenta of the electron and the bowling ball. So for the electron, this is 1.1 times 10 to the minus 24 kilograms, meters of a second. And for the bowling ball, this is 2.9 times 10 to the minus 9 kilograms, meters of a second. So I've just got to carry out the calculations of these ratios now. I've already done this. I got 0.6 nanometers for the electron wavelength, and I got 2.2 times 10 to the minus 16 nanometers for the bowling ball wavelength. So let's just make a couple of comments about these two wavelengths. The wavelength for the electron has the scale, the size scale of an atom. So it's sort of the size of an atom is the electron wavelength. By comparison, the wavelength for the bowling ball is many orders of magnitude, 10 to the 15 times smaller than that size scale. And so it is smaller than humans have ever seen, a size scale smaller than humans have ever measured. And so that's the two wavelengths that have emerged here. So, we do see wave properties of electrons. We can measure wavelengths, the effects of wavelengths at the size scale of an atom. We've never seen the wave properties of a bowling ball. We've never seen wavelengths of this size scale. Finally, we're going to compare these two wavelengths for our matter waves, the electron and the bowling ball, with the wavelength of light corresponding to a photon energy of 4.5 electron volts. So here we're going to use a different equation or a different relationship to get from the energy of the photon to the wavelength of the photon. The energy of a photon is related to the frequency of the electromagnetic wave by this little equation here, E equals Planck's constant times the frequency. In turn, the frequency is equal to the speed of light divided by the wavelength of the light. So we can replace the frequency with C over lambda. And if we look at this equation here, if we know the energy of the photon, we can calculate the corresponding wavelength of the light or the electromagnetic waves, knowing these two constants, Planck's constant and the speed of light. So let's just turn this equation around and write it as an equation for lambda equals Planck's constant times the speed of light, so two constants of nature, and that's divided by the energy of our photon. So plugging in the numbers now, I'm going to plug in Planck's constant. I'm going to plug this in, it's more convenient, in units of electron volts seconds rather than joules seconds. So it's 4.1 times 10 to the minus 15 EV seconds, multiplied by the speed of light, that's 3 times 10 to the 8 meters per second. Divide this by the energy of the photon in electron volts, that's 4.5 electron volts. If we look at the units here, let's just check through the units. We've got EV in the numerator and the denominator, that cancels out. We got seconds in the numerator and the denominator here, that cancels out. We're left with meters, which makes sense for a wavelength. And I've already gone ahead and calculated this wavelength. I got 275 nanometers. So this wavelength, it's longer than the wavelength of the electron waves. It's longer, much longer than the wavelength of the bowling ball waves. It's a wavelength, 275 nanometers is nearly visible light, not quite visible light, it's ultraviolet light. Anyway, this problem involved the wave-like properties of matter. It also involved actually the particle-like properties of electromagnetic waves. And in particular, it involved the de Broglie equation, which applies to matter waves, which relates the wave-like properties of matter to the particle-like properties of matter. Specifically, it relates the momentum of a particle to the corresponding wavelength of that particle.